Hello everyone, and welcome to another complimentary Green Tech Media webinar. Today's webinar is part of a series of webinars we do throughout the year to help key professionals in the solar, energy storage, and grid modernization markets stay informed through research and analysis on the latest technologies and market trends. Today's presentation is titled How to Retrofit Legacy Inverters, Issues, Solutions, and Case Study, and is brought to you by Chint Power Systems. My name is Lindsay Cherry, and I am a solar analyst here with Wood Mackenzie Power and Renewables, and I will be moderating today's webinar. If you enjoy our presentations, I would like to remind you that we're offering today's webinar attendees a special discount to Green Tech Media's upcoming events, including the Northeast Solar and Storage GTM Forum in New York, which will take place on March 11th, 2020, and GTM Solar Software Summit, which will be on April 28th, followed directly by our Solar Summit from April 29th through 30th in Phoenix, Arizona. Please don't miss an opportunity to take a deeper dive into the industry and network with key decision makers. Please use code WEBINAR for a 15% discount to these events. So before we get started on the presentation, I would like to take a moment to go over the screen in front of you. Speaker bios are now accessible from the top tabs by clicking on each speaker's name. You can use the link on the left-hand side of your screen to download a copy of the slides from today's webinar. Most importantly, please note the Q&A module on the left side of your screen. At any time during today's presentation, you can submit your questions for our speakers. We will have about 10 to 15 minutes of Q&A at the end of the presentation. So today's presentation we'll be hearing from speaker Stephen Bollinger, who is an applications engineer with Chint Power Systems, and Ryan Mayfield, founder and principal at Mayfield Renewables. And so with that, I'm going to start off with a brief presentation from GTM, and then I will hand it over to our speakers. So before I get started, I just wanted to give a brief summary overview of what I will be covering. So there will be an overview of the global solar market and inverter market. I will then go over the evolving inverter landscape and the implications of the solar markets on aging install base. So I wanted to give a quick overview of the current state of the solar market. So installations have been growing over the last few years, and in 2019, the market is finally exceeding 100 gigawatts DC of installations. So while the market will continue to grow, global installations by region will begin to shift. We will start seeing APAC occupy a much less significant percentage of total demand as we see China's installations wane. Other regions will pick up this market share, including Europe, Middle East, and Africa. So this chart here displays a bird's eye view of the solar inverter market as we see it today. So it details PV inverter shipments by product type and forecasts out about 5 years, and also details market value in terms of millions of dollars. And so needless to say, the inverter market is dependent upon the global solar demand. So global PV installations are expected to continue to increase through 2024. And of course, this correlates to inverter shipments within the same time frame. And so although from 2017 to 2018, we saw the PV inverter market value decrease by about 1%, and we expect that this will continue through 2024. In spite of this, we're seeing installations increase within the same time frame. So in 2018, I wanted to just briefly go over the commercial three-phase string inverter market. So we saw growth in 2018 spurred by installations in Asia Pacific and Europe. Europe's solar market growth in 2018 was really driven by commercial installations, which saw probably the most shipments of any sector in Europe. And the global three-phase string inverters will dip slightly in 2019, but we're going to expect them to continue to grow, and they'll be a stable part of demand through 2024. Installations in China's residential and utility sectors decreased from 2017 to 2018, although commercial three-phase string inverter shipments were the only product type that actually did not decline. Commercial shipments in the Middle East also declined, I should note. But we saw a big increase in South Korea, growing by 65% from 2017 to 2018. And now I want to just briefly go over the inverter landscape and future implications. So taking a step back, I wanted to highlight the shift in the industry towards higher voltage systems. So we've seen industry shifts from 600 volts to 1,000 volts to now 1,500 volts. And prior to 2013 in the US, 600 volt systems were the most popular. However, authorities began allowing for the use of 1,000 volt systems, and these systems became the most prevalent. In this chart, we can see that 1500-volt DC architecture has been growing in popularity in recent years and is now the prevalent architecture. Higher voltage systems allow for longer streams, meaning fewer combiner boxes and overall less labor. So overall, we're seeing this switch to higher voltage systems because it can lower costs by as much as 5 cents per watt overall, which is why we've seen these shifts in the last couple of years. So in 2018, North America had a very high ratio of 1000-volt to 15-volt systems. So about over 85% of installations were, I think, over 1500 volts. So as the solar market continues to grow, we'll see cumulative installations in the next 5 years peak over 1,200 gigawatts DC. So this cumulative installed capacity will, of course, be compiled of systems that have different architectures. And while it would be ideal that we install solar systems and simply forget about them and they work well, but we all know this is not true. Systems need maintaining and parts will need replacing. So inverters are more likely to fail, than any other component, some other studies have found. And so as the solar industry mature, there will be increasing opportunities for inverter retrofits. Wood Mackenzie estimates that by 2022, about 10% of installations will be 10 years or older, and there will be plenty of cases for retrofitting. For example, if a system is underperforming, the root cause could be inverter malfunction. Although inverters are estimated to require replacement every 10 to 15 years, the reality of the matter can be much more complicated, and issues with inverter warranties may lead to inverter retrofits. In some cases, even if an inverter fails within this warranty period, inverter vendors may have exited the market, leaving warranties unfulfilled. Other issues like extreme heat, cold, snow, hurricanes, and other weather events are frequent causes for damaged inverters, and these could also lead to inverter retrofits. And then, of course, replacing 600-volt inverters from these older installations that we discussed earlier. So with that, I would like to hand it over to our presenters today to talk about how to retrofit legacy inverters.
Great. Thanks, Lindsay. Hi, everyone. Thanks for joining in. This is Ryan Mayfield, and I will be starting us off here on our webinar on our topic today, how to retrofit legacy inverters. I'll go through the front end, and then Stephen will jump in and walk us through a case study. So as you know, the bios are over there on the side, so you're able to look us up there if you'd like. So want to start off with what our agenda is going to be, what we're going to talk about here today. So first off, when we're talking about retrofitting arrays, retrofitting systems, want to basically understand what the issue is. So looking at kind of focusing in on the inverters and understanding what those issues are for replacing inverters, kind of what the components, things like that. Then we're going to talk about some of what the solutions are, identify potential solutions. There's, as with any issue that you can come up with or that you're going to have, there are multiple solutions for the problem. And so trying to just wade through those and look at all the different options. Then if going through what we're going to see as far as the objectives of doing the inverter retrofit, what are the goals, might seem relatively obvious, on what the goals are, but it's always worth asking the question and making sure that the objectives for the retrofit are being met. And then we have a case study that Stephen will be able to walk you through, and then we'll go through and do those questions and answers that we've been talking about. So first off, the issue of the legacy or unsupported inverters. And so we have inverters that are out there. We're hitting a lot of, as Lindsay showed in those slides, we have inverters that are hitting that 10 to 15 year mark. And so the typical components, be they contactors, fans, and other components that are inside the inverter, they're coming to their end of their life. And so options are always to replace the components, and that's a possibility. And you may get a few more years out of the life, but without doing a wholesale replacement of those components, it can be difficult. You may be coming back multiple times to the site to replace different components over the life of the system. So another issue that we're seeing out there is the original manufacturers. A lot of them, as anybody who's been in the industry for any time, know the manufacturers. A number of those manufacturers that we were installing 10, 15 years ago are either completely not around, they've gone out of business, or they've been bought out by other companies, and sometimes the companies that bought them out have either gone away or are no longer in the industry or in the solar industry. So see a few of those there on the right-hand side of the screen. And so that can be a problem. And along with that, not having manufacturers either present or actively working in the industry, one of the problems with replacing components is just finding those components. So finding the compatible components that you can use within your existing inverter. And then another big issue that we're seeing, and this is one that I've been feeling personally, is limited tech support from the manufacturers. So even if they're around, they may be giving no or limited support on their products. It may be difficult to find somebody that's very knowledgeable on the older products. So those are all some of the problems of these manufacturers. And then those two kind of pieces combining into making it cost prohibitive on doing maintenance. So maintaining the inverters, replacing components becomes very cost prohibitive when you can't get good support or find those products. So with our aging systems, we have failing inverters that are out there, and causing system downtime, their loss of revenue or wasted resources. And we're focusing in a lot here on the larger commercial scale projects, and in many cases those projects have recouped their investment. Maybe their initial investment has been recouped, but there is lost revenue associated with it, and the initial financials were very often based on long-term projection of this array operating. And you have modules that have 25-year power warranties, and you have inverters that are potentially failing in the field. And so that's just is a loss of revenue. So it's a potential way for the system owner to be making money, but that is without the system operating. And then, of course, we have these wasted resources. They've put in a lot of time, money, and effort. Maybe they've put them in for various reasons, and if there's an array sitting out in the field or up on a rooftop that isn't being utilized, then there's just a resource that's being wasted. And now, it's easy to say, and it's probably hard in reality, but asset owners really should be planning for these inverter retrofits. What I've been seeing personally in my practice is there's a lot of systems where we are getting asset owners that are reaching out to us, and the systems are either underperforming or not performing, or the asset owners don't even know if they're performing at all. And they very well could be the second or third owner down the line. The land got sold, the building got sold, something like that. So you may be coming across these, and maybe even new asset owners that don't realize that these are components that have an end of life. They need to be maintained, and they should expect that there's going to be some ongoing costs with those. And then one of the final kind of issues here is, as already been mentioned, the shifting of the industry from 600 volts to 1,000 volts on our DC inputs for our inverters, and now for a lot of our ground-mounted arrays moving even up to 1,500 volts, and likely going to move past that in the years to come, higher voltages. So these are all part of the issue, the fact that we have these systems where the industry is moving away from where we originally were, and so needing to think of that as we are coming up with different solutions. So now, as far as the objectives go for an inverter retrofit, we need to be thinking about a few things. And some of the objectives this by all means isn't going to be every single objective in every single case, but code compliance is definitely a big one. So we want to make sure that the new system or the updated system that we put in is maintaining any electrical codes that we're subject to, and then satisfying electrical requirements. So if there are any specific site electrical design requirements, need to make sure, think about the interconnection, for example, in a certain case. Minimizing rework is always a goal that you should have, an objective and a goal. Maximizing system uptime, so being able to, again, keep that system up and running, generate revenue for the asset owner, and then maximizing production goes hand in hand right there with the uptime. And then one of the big things too to consider is future O&M costs. So this is just going to be one of more O&M issues for any of these aging arrays moving forward. So looking at the system as a whole to try and minimize those O&M costs. Now, as far as code compliance goes, the inverters, the current generation of inverters that we're talking about putting in are really going to meet the key requirements that may not have been in place when you originally installed the system, or you or somebody else when the system was originally installed. So the big ones being arc fault and ground fault. Those are going to be integrated within the inverters. The inverters we're speaking to directly, string inverters, 1,000-volt string inverters, will have those built in. And so really the big question at that point becomes the rapid shutdown and what the requirements surrounding rapid shutdown will be for if you are retrofitting an array. And so I know it's a tough one to sometimes to address, and talking with your local AHJ is really the best option to figuring out what the requirements, if they're going to require that you bring it up to local or to current codes. I've gotten multiple answers when I've asked the question, and so really that is the best to do is to check in. If you're still under 2014, adding, you get a lot more flexibility in terms of locating the inverter close to the array, possibly. If you're in 2017 and the requirement is to bring it up, then that's going to be a lot more rework, and we'll talk about that when we get into some of the solutions for the different types of systems. Now, when you are moving forward with doing a retrofit or on an array in a system, a site visit is highly recommended. The single line drawings, the existing as-built drawings, rarely are they a super accurate match for what's actually going on in the field. And considering that these are components that have been in the field for 10, 15 years, it's probably worth taking the time to go out there and look at it. So take a look at the type of inverter, make sure that it matches physical layout, and then it's worth spending some time with the original manufacturer. So try to get a hold of them. Is there support? Can you get replacement parts? Is there a path without having to completely gut out the system that might be worth exploring? The system architecture is a big thing to make sure that you're looking at, the electrical design of the system, what type of inverters. So one of the things that you may run across a number of bipolar inverters, for example, were out there in the field. And so what do those strings look like? We'll talk a little bit about fuse servicing or fusing the strings and things like that when you look at replacing inverters. But understanding what's actually out there, what are the combiners like? What do you have are there recombiners, fusing? All that kind of stuff needs to get really known before trying to figure out what the solution is. And then my big recommendation is, always evaluate the whole system. Don't just hone in on the inverters. If you're getting if you're getting error codes out of the inverter and it makes it relatively clear that the inverter is failed, that's fine, but you should be looking at the entire system, looking at the array. Are there issues with the wiring? Because if you go through and replace the inverters only to find that there's ground faults out there somewhere in the field, and then all of a sudden, the client's already spent a bunch of money and they're going to expect that the array is operating, and so it's kind of can snowball on you. So make sure that you're evaluating the whole system. Are there any modules or any issues with any of those or anything like that? So making sure that you spend some time doing that. Now, some of the solutions. So, some solutions that are out there, one would be retrofit with a 600 volt inverter. And that is potentially an option, but could be very difficult to find, much like our friend the Panda Bear here. So might not be an option, and if you do find some 600 volt inverters that would work in your scenario, it's highly likely that they're going to be very, very small string inverters, relatively small, 15, 20 kilowatts maybe. And so finding those might not be the most ideal situation. And then it gets back into the issue of the industry is moving away from 600 volts anyway on our commercial systems. So you're kind of staying with a technology that may not be the most up to date. And then future O&M, sticking with that 600 volt because of the way the industry is moving will make it more difficult in the future. Another option could be retrofitting with optimizers. This is likely mentioned earlier with the rapid shutdown. This is very much a solution that may be required if you are required to bring up to current rapid shutdown requirements. One of the benefits is you could actually get the ability to operate your array closer to the 1,000 volts. What you need to do in this case is look at your modules, look at the optimizers, look at the DC to DC converters if they're not optimizers, but look at the components, look at the inverters. Make sure that everything's playing nicely together. One of the issues in a lot of these arrays will be that your array, your modules within the array are only 600 volt rated. So making sure that the wiring, the modules themselves and the wiring associated with those aren't going to be subject to seeing 1,000 volts. So that's, looking at the optimizer specifically. This will require an entire rewiring of the array because now you're putting on components on each individual module, and the output of those needs to be moved from 600 volt. The output wiring, I should say, needs to go from 600 volt to 1,000 volts. So there is likely home runs that needs to be reinstalled and brought up to the current 1,000 volts. And then there's the issue of added reliability. So the more components you put in the system, you're just adding more failure points. So there are some potential issues with adding the optimizers or power electronics to an aging system in that sense. And then there's the connector compatibility issues. Those are something that we need to be thinking of. It's probably on a lot of people's minds given some of the news that we've been seeing as of late in the solar industry. So on our older modules, 10, 15-year-old modules, you may have those old MC3 connectors. And so now all of a sudden you're trying to connect an MC3 module to an MC4 or an Amphenol, whatever it is on the optimizer. So there can be some issues there. So that can make it more difficult to just swap those out. And then there's a third option of doing a retrofit with 1,000 volt inverters, and that's what we're really here focusing in on today. And so with the 1,000 volt inverters, the rule of thumb that you can use is that a 1,000 volt inverter operating on a 600 volt array, you essentially get 60% of the rating of that inverter. So if you have a 50 kilowatt inverter, 50 kilowatt 1,000 volt inverter operating at 600 volts, it's really going to operate more like a 30 kilowatt inverter. So when you change these out, you need to be thinking about voltage windows, very specifically on the inverters. And so the startup voltage is a very big thing that you need to think about. And so you need to make sure that the open circuit voltage of your 600 volt array is enough to wake these 1,000 volt inverters up. And so if the array was originally installed with a very, very low voltage, if it was at the bottom end of the 600 volt window, then you may have a risk of not ever even being able to turn on the inverter at 1,000 volts. So that's one of the things you really need to pay attention to. And because of the nature, because of the input voltage being a function of the ability for the inverter to put power out, you are going to be basically going from an inverter that is power limited to one that's current limited, so that you will that's going to be another function of the power reduction. One of the things a good suggestion to do is if you are installing say a 50 kilowatt inverter, you will likely want to reduce its power output, the settings to reduce the power output, such that your interconnection, the power output of that inverter is actually matching your interconnection agreement. It matches the overcurrent protection devices. It matches the conductor sizes. So by doing one small change, you're able to keep a lot of the existing system components and specs within what they were originally. And then one of the big things to do is make sure that you're labeling this. Of course, you're going to have some NEC labels, but one of the ones that is highly recommended too is adding this maximum power kilowatts on the inverter. So if you have again, 50 kilowatt inverter that's been through the settings of the inverter reduced to a 30 kilowatt inverter, you should note that so that somebody coming up behind you in 10 to 15 years doesn't try and do something to undo what you've done. Okay, and so some of the benefits for the 1,000-volt retrofit. And so, again, minimizing rework is always going to be a goal, and maximizing system uptime. And so, if you have an existing string inverter, and there were a lot of those, there were a number of inverters out there at the time, 20 to 30 kilowatt range. So this is a perfect swap out. You take a 50 kilowatt inverter, you're able to put it in place of some of these 23, 20, 25, 30 kilowatt inverters. It should be relatively quick if the wiring was all done, and the strings, you don't have to do restringing, anything like that. It can be a pretty darn quick process. But again, knowing what the system was, if it was a bipolar inverter, something like that, you need to make sure that you're going through in the field and doing the necessary changes there. If it's an existing central inverter, then you're going to have to add an AC panel, because now you're going to have a number of smaller inverters, so you're going to have to aggregate the AC output. But on the DC side, it's very likely that you're not going to have to change anything. So that's a nice benefit of doing these retrofits. And then maximizing production. So we're going to be able to put in an inverter that has a greater efficiency than original. And then the additional maximum power point trackers will give us the ability to look at our array, maybe do some module replacements a little easier, and be able to have a better way of updating the array if that becomes a problem. So the thing as far as the efficiencies go, the 1,000-volt inverter operating at 600 volts, it will be by nature a little bit less efficient than what the peak efficiency is. And again, that's just a function of the input voltage versus the output power and the efficiency curve. So these inverters want to operate closer to their maximum voltage, and just by nature of the system, we're not going to be there. But by removing an isolated inverter, an inverter with a transformer, with these and replacing with these higher efficiency inverters, you're going to gain some efficiency. You're still going to see yourself 1 to 2% above what the original inverter was. So even with the fact that you're not operating the new inverter at its optimal point, you're still going to be better than what you were at with the old inverter. And then as far as minimizing future O&M, one of the big things, again, the industry moving towards the 1,000-volt, 1,500 volt. So we're kind of keeping up with the times, if you will. And then the other thing is, if you have modules that you're going to be replacing, I've been going out on a lot of sites, been seeing a lot of modules, individual modules failing within, or group of modules failing within this array, and then going and finding those same modules is nearly impossible anymore. So by replacing these inverters with string inverters with more maximum power point trackers, you can see that basically the number of strings that are either need to be replaced or at risk are reducing. So if you have a single 250 kW central inverter, it's like one big MPPT, all the modules need to be basically at the same point. Whereas if you take that single inverter to 7 string inverters, but that those string inverters still only have 1 MPPT. Now you've reduced the number of modules that are at risk if you're needing to replace the inverter. And yet again, if you make it a little bit more granular, take it to 3 MPPTs on those 7 string inverters, then you're reducing the number of modules that are kind of at risk, if you will, just down, making by using the more granular and the multiple MPPTs. So you're able to look at having a better options if and when the modules need to be considered as far as replacements. And then one of the final things that I'm going to talk about is just really other technical issues. And so ungrounded arrays, the ground fault protection is more accurate than what we had with our transformer-based inverters. And so you're actually, as far as safety goes, you've increased the safety. You're going to have the arc fault protection in there. There's just additional safety features that you're improving the system safety and reliability in that sense. And the thing to note with going back to your system type is if there is fusing in the on the string level, then the 2017 code gives you some allowances that makes this retrofit a lot easier than if you're in the 2014 code. So just knowing your code cycle is important. And going back again, just making sure that you understand the complete system. And then finally, PID for floating arrays with older modules. If this is of a concern, then the recommendation is talking with the module manufacturer, making sure that they haven't seen any issues or that there's any issues there. If it is an issue or if it's of concern, there are PID boxes, things that are able to be added into the system that can help reverse those effects, and so that would be something to consider. Consider adding to the system. So with that, I will turn it over to Stephen, and he's going to walk us through this case study for swapping out a central 600-volt inverter with 1,000-volt strings.
Thank you, Ryan. I'm Stephen Ballinger, application engineer with CPS. We are going to talk about a retrofit at a Big B manufacturing solar farm in Pennsylvania. You see a picture on your screen of the site, and the inverter on the right-hand side is the replacement inverter. There were 4 existing inverters on the site. They were installed 2011 timeframe. The retrofit company installers were Endless Energy. They approached us, asked us if we could come up with a solution. We did the simulation and decided that we would simulations penciled out, and so we thought we would go ahead and suggest using 1,000-volt string inverters to replace the ailing central inverter. So the existing system consisted of 4 260-kilowatt PV-powered central inverters. They were 480-volt output and 400 amp. 480-volt output was perfect for our 3-phase string inverters. This inverter had 600-volt input from the array, 12 inputs. The inputs consisted of string combiners. There were 8 strings on each combiner, total of 96 strings on the inverter. One of the facts about the array that we weren't aware of, because we personally didn't do a site visit, the retrofit installer took care of all that, but we were not aware that there were actually optimizers on each module. So anyway, that'll come up a little bit later in the discussion, but you can see a little block diagram basically that shows the inverter, 400 amp feed output for the inverter. So why was the inverter in need of replacement? The inverter had actually failed, was down, and you'll see later in our analysis of the performance that the inverter had poor performance for approximately a year, and several months out of the year was actually producing no energy at all. We really don't know the repair cost of that inverter. You could probably do back of envelope calculations and figure out how much the loss of revenue of 25% of the system would be, but we knew that the OEM cost was quoted at $16,000 per year per inverter for this site. So given the fact that this inverter was failing and troublesome, the owner decided to pursue a retrofit. So what did the retrofit consist of? Well, we put in 6 50 kilowatt 1,000 volt string inverters. Of course, that totals up to 300 kilowatts. The existing inverter was 260, so we derated the output power of the inverter to make sure that we weren't no more than 260 kilowatts. Let me see the next. This kind of shows you the retrofit in a schematic type format. We installed a 400 amp AC panel with 6 60 amp circuit breakers that allowed us to use the same feed, the 400 amp circuit that was feeding the old inverter. On the input, there's 12 combiner inputs, so we divided 2 combiners into each inverter. So there was no need to rewire the DC side as well. In this picture, you can see a little box here. We'll show it a little bit later in detail, but there's a little box here that was existing. And that was basically a splice box for the old central inverter. And finally, we removed the ground on the negative polarity of the existing array. The string inverter topology only allows for a floating array, so we had to remove the ground. So here's a pictorial view of the old inverter. There's actually 3 of these still on site. And you can see the existing DC wire box that went into the inverter, and you can see that we reused that in this retrofit. And you can see the new AC panel at 400 amp feed coming into this panel. I might comment that the structure here was not necessary. I mean, these are string inverters, outdoor rated, but the owner is a steel fabricator, and they wanted to build a little house for this retrofit, and did a very nice job. So if we look at the production comparison, obviously you want to make sure that the new inverter is performing as well or better than the existing inverter. So we looked at the performance of the system for the entire year, starting in January. And in this bar graph, you can see that the green bar is the inverter that was replaced. You can see the down months by the arrows, very low production in those months. And the inverter was replaced in September. And then the blue bar is an existing inverter that's still at the site, has the same array orientation, and also has the same DC input power. So it would be a very comparable scenario to compare the replacement against the inverter represented by the blue bars. The orange and red bar are 2 other inverters. They're slightly different orientation and have different DC input for those inverters. So you can see that after the replacement in the month of September, the green bar was slightly lower than the blue bar, but that's because the whole month of September was not a production month because the inverter was replaced, I believe it was the first week of September. And of October, you can see that the production was equal to or approximately equal to the production of the inverter that is equivalent in input power. So we also looked at a full irradiant day, the production on a full irradiant day. This histogram is maybe a little bit complex to explain, but we took the two inverters that had similar arrays attached. We took the average of the 192 strings, 96 for each inverter, and we figured out or plotted a histogram of the number of strings as a percentage of that total average. And you can see the orange is the old inverter, and it pencils out it's a little bit less than the new inverter. The difficulty here is that, like I mentioned earlier, there are optimizers on each of the PV modules. And when we drilled a little deeper in our analysis, we found that there were some issues with production at the string level. So basically, you can see that in this histogram as well. You can see there are some strings that are performing much less than the average. So those are the issues that are still existing with the array. One of the other issues that we felt it was necessary to analyze would be the compatibility of the inverter and the stability of the inverter when operating with the optimizer. So we did a string, at the string level, we did a comparison between, on the same day, pretty much a full irradiant day, between the old and the new inverter. The things that we observed here is that the old inverter appeared to have some stability issues when operating with the optimizers, and that can be seen by the erratic production. The other thing that we noted here was a production droop in some of the strings in full irradiant day. Not sure why this occurred. We haven't been back to the site to try to analyze that. We did recommend that they could possibly look at the array and look at maybe sorting out or disconnecting or wiring around the optimizers. We feel like that if that's done, we get a no midday droop, so you would obviously get an increase in production. We feel like if you remove the optimizers from this particular array, you would get an increase in reliability because you've significantly lowered the component count, the electronic component count, and the stability that we noted in the performance should be not there. It should be eliminated. So I guess the big conclusion here is, I mean, if you assume that there are equal issues in both arrays, whether it's the optimizer not producing, because when you drill down to an optimizer or PV module level, you see some modules are not producing, whether that's an optimizer or a module issue, we do not know. But we feel like that if you assume equal issues in both arrays, then you get a better than new solution with the CPS retrofit. If for no other reason your OEM issues go away, if you need to repair, if you have an inverter failure, you only lose a sixth of the array. There's separable wire box, so you have a 15-20 minute, once you get the part on site, time to repair. And one thing we'd like to stress is that, every retrofit that we've looked at so far has a slightly different twist to it. So you need to do a site visit, and you need to design to the specific variables that you see at the site. Basically, there's no rubber stamp, silver bullet solution, and one size definitely doesn't fit all. And in summary, it's obvious that aging and unsupported inverters cost money. They cost money through loss of production, system downtime, O&M cost. And we feel like the best solution for the 600-volt retrofit is to replace it with a 1,000-volt string inverter. As long as you've done your homework and make sure that the voltages in the array are going to allow the inverter to start up, we feel like that's the better solution because of higher reliability, and it can be done with little to no rewiring of the array. So we feel like it offers better than new performance, obviously low life cycle costs, and you have a brand new warranty on the product. So with that concludes our technical presentation. If you need a retrofit, CPS is here to support you along with Mayfield Renewables. And I'll turn it back over for our question and answer session.
Well, thank you so much, Stephen and Ryan, as well, for a really fantastic presentation. It was really informative. And we've gotten some great questions that have filtered in throughout the presentation. So I'll start asking, but before I do that, I just want to remind everyone you can still submit your questions through the Q&A module. So please do so, and we'll try to get to as many as we can. So let's see. So the first question we have, I believe, for Ryan is it possible to replace a 600-volt central inverter with a 1,000-volt central inverter? And if so, do you recommend that as a solution?
So yeah, replacing a 600-volt central with a central, essentially, would definitely be an option. I think some of the things to consider would be just long-term, as we talked about, the granularity of those arrays. And so, if you're combining all those strings into a single input, I think that is somewhat leading you to, as we saw in the case study, you had a fourth of the array that went down because of one inverter. So there's that aspect of it. And so by all means, it's a possibility. I think it's just worth digging into, looking at both options and seeing what the dollars and cents come out to in terms of replacing with, I would say, more readily available, more options, more different aspects of if you do it with a string inverter.
Thank you so much. And then another question we have from the audience is, what is the lowest minimum startup voltage of these inverters?
So I know with the CPS. Oh, you go ahead, Stephen.
It comes from the factory at 330 volts, but it's adjustable down to 300 volts. And it's not really a hard and fast turn on. There's also another component of minimum power. And what we found at this site, where there are a few days in September, where the morning temperature was fairly high. The open circuit voltage was a little bit less than 300, but the inverter started up fine. And so, it's basically a combination of the startup voltage and the minimum power.
Great. Thank you. And another question we have for Ryan, I believe it is, what does it mean to derate an inverter? Is that a software setting change, or does that require additional equipment?
No additional equipment is required. So what we're referring to a derated inverter is just reducing its power output. So again, not allowing the inverter to put out any more power and current than what you want it to. So again, if you're replacing a 30 kilowatt inverter and it has the amperage output, you may want to take your replacement 50 kilowatt inverter and not allow it to put out any more power and current than that existing one, and then you can just do a clean swap on it.
Mm-hmm. Thank you so much, Ryan. And Stephen, a question for you. What did you do differently to remove the connection between the grounded conductor and the grounding conductors?
Actually, I'm not sure exactly how that was done at the site, but when we turned the site up, we were actually there for the turn up. We made sure that the negative polarity was not grounded. I believe it was grounded at the string combiner box. But we also we had that string interface, DC interface enclosure. There may have been a ground there, but it was no difficulty at all removing the ground.
Thank you. And Ryan, the next question is for you. If you were going to connect a 1,000-volt inverter to an array that was previously connected to a 600-volt input inverter, how do you calculate the new maximum power output?
So the maximum power output on those inverters is, a good rule of thumb without knowing a whole ton would be 60%. You'd get 60% out of the new 1,000-volt inverter. What you really should do and can do, inverter manufacturer CPS has DC input to power output charts, and so you would just need to go look at your specific example. If your array is operating at 350 volts, you'd be able to go look at the 350 volts versus the power output on the 50, 60 kilowatt inverter and be able to determine what the actual power output is.
That's great. And we had, Ryan, I think the next question will also be directed towards you. So we had a couple questions trickle in about NEC 2017 code requirements. So what does Mayfield Renewables and CPS recommend? Would you be able to reiterate that for us?
Yeah, so if you are looking to get, the 2017 requirements, if it's a ground mount system, you're covered. I can't think of anything that is going to be in 2017 that this inverter won't, that the CPS inverters won't work for. The big one would be a rooftop system, where you are now subject to rapid shutdown requirements that you weren't subject to before. And the CPS inverters have the SunSpec standard, and so you would be able to you would have to be looking at matching the inverters with the appropriate DC to DC optimizer, or not optimizer, but power electronics in order to meet that requirement. And so unfortunately that means a piece of power electronics per module that's getting installed with this entire, with the inverter retrofit.
Okay, thank you so much. And Stephen, I believe the next question is for you. What about replacing a central inverter with a non-nominal AC output voltage, say 380 volts AC? Are there any options other than replacing the pad mount transformer?
There are no other options. I mean, the output of the string inverters is 480 volts, and so you have to have a 480 volt transformer.
Okay. Thank you. And Stephen, I believe the next question is also for you. Is there a solution if you cannot hit the startup voltage under normal STC conditions? If a site came up with that kind of issue, we would have to try to determine how far off the startup voltage, the minimum voltage from the array would be at open circuit. We'd probably go back to our R&D organization and find out if there was some way of
of determining what the minimum power startup, because like I said, we thought we had a couple of days out of the year where we might not start up at this retrofit, but as it turns out, I mean, they were like 295 volts, and the inverter started fine. So I think to say there is no solution is probably not the right answer, but I think it's probably a case-by-case basis.
Okay. And do you have, I think Stephen or Ryan could probably answer this, do you have experience converting vintage PV systems with central inverters to island-capable PV systems with string inverters and battery?
Our inverters are grid connect inverters, and that's no. The answer is no. We don't have experience in that, and the other answer is we don't have inverters that will island. We are introducing inverters as part of energy storage, which is a totally different topic.
Right. Yeah, that's what I was going to say. Is that there's the energy storage options that CPS has been rolling out, and yeah, it sounds like a fun project. Those would be interesting projects, but definitely a case by case basis, and but fun things to work on for sure.
Okay. And Stephen, the next question is for you. With central-to-central replacement, how do you deal with landing the new central inverter on the existing slab conduit's footprint? Presumably, one may need to break out the concrete slab and realign the conduits, possibly need to replace short conductors too. Do you have any thoughts on that? Or that actually might be for Ryan.
Yeah, I mean, I can address that. I mean, we looked at going into the central inverter market, but we do not offer a central inverter in the U.S. market, and so it would be difficult to answer that. But it's definitely a mechanical application challenge.
Yeah, exactly.
Okay, great. And I think we have time for just a few more questions. So let's see. So Ryan, this next question will be directed towards you. How do you size the inverters as a formula of the expected input current and voltage?
So really, it's a function of looking at the input voltage. What do I have to work with? And trying to match that up with our 1,000-volt inverters. And the current and the power are likely not major issues. You definitely need to pay attention to them. But just because of the string inverter aspect, we're able to, as long as there aren't combiners out in the field that are combining a large number of strings, it's pretty easy to peel strings off and put them into the appropriate MPBTs. The issue does become if you do have string combiners that are combining, a lot of strings, then that can become more of a problem in terms of that. But you could also end up putting the inverters where the combiners were, and so there are options in that sense.
Okay. And one more question. So lastly, can you use the solution with positively or negatively grounded PV? What about floating PV that has a ground on the bus?
Well, that sounds like a three-part question. The negative and positive grounded arrays, we would just remove the ground from the array, just like we did at this site. The last part of that question, I don't know how you have a floating array with a ground. I'm not sure I understand that.
Okay. Well, with that, it is 3 p.m. on the dot. So thank you again so much for this wonderful presentation and for this great Q&A. Greatly appreciate it. Thank you for our audience for joining us, and we hope to host you guys soon. Thank you.
Thank you.
Thanks.